In this lesson, I'll show you how to solve electrical problems by the Laplace transform. This is question number 1. The question reads, a capacitor is discharged through a resistor by throwing the switch from position 1 to position 2 at times equal to 0. Find the current I. Take a look at this circuit. What we're doing is we're taking it from position 1 to position 2, and they want us to find the instantaneous current. To do this problem effectively, you need to keep in mind Kirchhoff's voltage law, which states that the sum of the voltage that drops across a resistor or an inductor or a capacitor in an electrical circuit must be the same as the voltage source applied to the circuit itself. The voltage being applied is 115. So what we have to do to represent this is find out the drop of voltage here plus the drop of voltage here and make that equal to 115. Before I do that, you need to know something else. The instantaneous current in a capacitor, over here, equals the voltage C times the rate of change of the voltage. And that's shown right here, where the instantaneous is equal to the capacitance times the rate of change of voltage. Integrating this expression gives us the voltage across a capacitor of the capacitance C, and that's shown right here. So to represent Kirchhoff's voltage law, I'll write down R times I, which is Ohm's law. The resistance times the instantaneous current will give us the voltage, plus V sub C, which I'll replace with 1 over C times the integral between 0 and t for the function I dt is equal to 115. The next thing that I'll do is replace this C with what it's equal to, and it's equal to 125 microfarad, but we can't use microfarad, we have to use farad. So to change that, we need to write 125 times 10 to the power of negative 6. That takes the place of C. What takes the place of R is 1,540 ohms. So let's go ahead and write that down. 1,540 times I plus 1 over this number gives you 8,000. 8,000 times the integral between 0 and t, I dt is equal to 115. The next thing is to take the Laplace transform of each of these terms. Taking the Laplace transform of this gives you 1,540 times the Laplace transform of I, plus we have to take the Laplace transform of an integral, and we've done a video on this in the past. What you do is you simply take your function and write it as the Laplace transform of what the integrand is. Then you take your coefficient, which was on the outside, and divide it by s. And this is equal to 115. So if we take the Laplace transform of 115, we'll also get 1 over s. It's the Laplace transform of a constant. And then you take 1 over s and multiply it by 115. Next, we will solve for the Laplace transform of I and rewrite our expression in the form of a table entry. And what I'm referring to about the table entry is one of these. So let's go ahead and do that. I'll solve for the Laplace transform of I. By factoring it out, we get 1,540 plus 8,000 over s is equal to 115 over s. Dividing both sides by this expression gives us the Laplace transform of I is equal to 115. And pretend that we found the common denominator amongst these two terms. We would have one denominator, that's s, and an s over here. So by dividing this expression by this expression, this s and this s will cancel out, leaving you with 115 over 1,540s plus 8,000. This transform looks somewhat similar to transform number 9, where you have s minus a. In other words, if we factored out 1,540, we would end up with s plus 8,000 over 1,540. And at the top, we would have 115. This reduces down to 0.0747 over s plus 5.19. Our a value here has to be minus 5.19 because to model this, this has to be negative. and therefore our function for current is e to the power of negative 5.19 t times that top number. This represents the answer, and there you have it. That is how to solve electrical problems by the Laplace transform.